Hi, this is Mrs. Villette, and we're going on to our next objective. We're moving on to inverses in section 9.2, and we will be finding the inverse of a function. There's quite a bit of text on here, so please pause and take your time reading it. For any function, for a one-to-one function that is, we can find an inverse function by switching the coordinates of the original pairs of the function. We've already seen this idea with graphing the square root function versus the x squared function. So for example, on the square function, we had points 2, 4, and then on the square root function, we had 4, 2. So we've seen this concept a little bit before. We need to know that the notation looks like a negative exponent, but it's not. It's read f inverse. So the inverse function, we read that as f inverse. We really need to pay attention that f inverse is not the same thing as saying 1 over f. If we wanted to say 1 over f, then we would write the exponent on the outside. So if we wanted 1 over f, we would say, so let's say 1 over f of x, we would say f of x, and then put parentheses to the power negative 1. It's a subtle distinction, but it's actually quite important. Okay, how do we actually go about finding inverse functions? Well, we're just going to switch the coordinates. So the domain will become the range. So the domain of f is the range of f inverse. Then the range will become the domain. So range of f is the domain of f inverse. So if we have a one-to-one function and it has ordered pairs x and y, the inverse will have ordered pairs y and x. So let's go ahead and take a look at a function that's just defined by a set of ordered pairs. So our function g has the ordered pairs 3, 4, 6, 2, 2, negative 3, 4, 5. First thing we need to check is it one-to-one? They say it is, but let's just double check. For one-to-one, we're checking for no repeated outputs. So my outputs are 4, 2, negative 3, negative 5, so it is indeed one-to-one. Just a quick check to make sure there aren't any repeated inputs. Okay, good, it is a function. The function that we're going to call the inverse, we will call g inverse, and it will be the set consisting of ordered pairs 4, 3, 2, 6, and so on. So we're just switching our ordered pairs on our g function. So that's pretty straightforward and pretty easy. Just swap the x's and the y. Now we're going to talk about finding equations of inverse functions. So this is not quite as easy. We won't have ordered pairs anymore. The thing that we need to remember is we're just switching x and y. So our strategy is going to go like this. First, we're going to replace the f of x, our function notation, with y, because f of x means y. Then we're going to swap x and y, so interchange them. Solve that resulting equation for y, and then the equation that we come up with, we're going to call that the f inverse. It's best to see this with an example. I'm going to walk you through this example that's already complete, and then we'll do one on our own. So the first step is my f of x. So we're going to find the equation of the inverse of f of x equals 6x subtract 1, and then graph on the same set of axes. So notice in this first step, instead of f of x, there is a y. So we replace the f of x with y. In step 2, x and y have been interchanged. So where there was a y, I've written an x, and where there was an x, I've written a y. Now we are going to solve for y. So notice the next step that was outlined here says 6y equals x plus 1. Really what they've done is they've moved this one over to the other side and then just swapped the side so that the 6y was written first. Then to get y all the way isolated, we divide both sides by 6. And the last step is to replace the y now with f inverse, because through this process of swapping x and y, we've actually found the inverse function. And now we are going to graph these. So our f of x, we will graph in blue. And this is, again, a line. Notice 6x minus 1 is in mx plus b form. So the y-intercept is at -1, and then the slope is 6. So I'm going to count up. I'm just assuming this is a scale of 1. 1, 2, 3, 4, 5, 6, and then over 1. Okay, so there is our first function. That's my f of x. Next, I'm going to graph my inverse function. Notice my inverse function is x plus 1 all over 6, which I could actually rewrite as x over 6 plus 1 over 6, or 1/6 of x plus 1 over 6. Now, it's not that advantageous to have the y-intercept as a fraction, but at least we can tell that the slope is 1/6. One point that I can easily tell is on this function is if I put x equals 5, that will make the numerator 6, and then 6 over 6 is 1. So I've got the ordered pair 5, 1. We'll go ahead and plot that. And then we'll use the slope of 1/6. Since I don't have space to go up and right, I'm actually going to go down 1 and then left 6. And then that is my f inverse of x. Now something you should notice, we had this point 5, 1, and we had this other point -1, 0. If we look at the original function f of x, it has a point 1, 5 and 0, -1. That's what we expect to see. We expect to see the x and the y coordinates swapped. Now another thing you might notice is that there's some symmetry, that these look like they're reflections of each other. And they are in fact reflections of each other, but not reflections that we have studied yet. So we've studied reflecting over the y-axis or the x-axis. These are reflections over this dotted line here, which is the line y equals x. Remember, we started by swapping the y and the x, so it makes sense that they should change over that line. And if you look, the corresponding points are actually perpendicular to that line. And so they're equidistant from that line. They're actually forming an isosceles triangle there. Okay, let's do another example where it's not all the way worked out and we actually have to do the steps. So we're going to find the equation of the inverse of f of x equals x cubed subtract 1, and then we'll graph them both. So we start by replacing our f of x with y. So we say y equals x cubed subtract 1. Next, we interchange x and y. So x equals y cubed subtract 1. Then we're going to solve for y. So I'll add 1 to both sides. X plus 1 equals y cubed. And if I want to get the y by itself, I need to cube root both sides. And of course, the cube root of y cubed is y. And the very last step is to replace the y with f inverse of x. We'll also switch sides when we do this. So we'll say f inverse of x equals the cube root of x plus 1. And then that's our inverse function. On the next page, we're going to graph the original function and the inverse. So we're going to graph f of x equals x cubed subtract 1. The best way to go about this is probably just to make a table of values, and we'll make values for x between -2 and 2. So if I take -2 cube it and subtract 1, I get -8 subtract 1, which is -9. I'm going to go ahead and fill in the rest of these values. You should pause and try to fill them in yourself and then check. So here are our values, and then we'll plot what we can on our axes. So -2, -9. I don't think we'll be able to fit that one, but -1, -2 we can fit, and then 0, -1, 1, 0, 2, 7. Now we know that this should be a cubic, so we have a basic idea of what the shape should look like. So there's our cubic function. To graph the inverse, we simply need to swap the x and y values. So for example, I need to plot the point instead of -2, -9. I will be plotting -9, -2, -2, -1, -1, 0, 0, 1, and 7, 2. And there is our inverse function. Now, one thing that we should notice is, similar to the last example, these two graphs are reflections over the line y equals x. And notice I've changed the original function to be blue. So here's my f of x, and then my red is my f inverse of x. Okay, now we're going to consider a situation where we can't actually take the inverse as the function is, but we can make some adjustments to make it invertible. So we're going to consider f of x equals x squared, which is not 1-to-1. It doesn't pass the horizontal line test, so it's not invertible. However, if we restrict the domain, it will be invertible, and we'll be able to find the inverse. So let's go ahead and create a graph of f of x equals x squared. So here we have our graph of f of x equals x squared. And we can see quite clearly that this does not pass the horizontal line test. So we've got a horizontal line going through there. It does not pass that. However, the directions say if we restrict the domain to x greater than or equal to 0, it is invertible. So that would mean actually erasing this left-hand part of the graph. So if we say that this is our function with a restricted domain, x greater than or equal to 0, now it does pass the horizontal line test. And if we think about taking this ordered pair, 0, 0, swapping the x's and the y, that would still be 0, 0. 1, 1 would still be 1, 1. And then 4, 2, 4 would change to 4, 2. And this should be a function that we already recognize. This is my f inverse of x, which is the square root of x. And of course, it has y greater than or equal to 0 and x greater than or equal to 0. Our previous one, we restricted the domain, but the range was already y is greater than or equal to 0. Algebraically, this is what it would look like. F of x equals x squared for x greater than or equal to 0, y greater than or equal to 0. Then we change our f of x to y, so y equals x squared, and again we have the x greater than or equal to 0, y greater than or equal to 0. We swap the x's and the y, and we're going to do this in the domain and range as well. Then we solve for y. Now normally we would get y equals plus or minus square root of x. However, we have this statement right here that y is greater than or equal to 0. So if y is greater than or equal to 0, we're just going to take the positive square root, and that's our f inverse. So our f inverse of x is just the positive root of x. Just so that you can see what happened with that plus or minus square root, I want you to take a look at y equals x squared, which is in blue here, and notice I haven't restricted the domain on this in Desmos, so I just have entered y equals x squared. If I simply swap the x and the y and I enter x equals y squared into Desmos, what I get is this parabola turned on its side. So actually this is the full inverse, but notice it's not a function. So the original function in blue not being 1-to-1 means that it wasn't invertible. Now what that really means is we can't create an inverse function, but we can create an inverse relation. So notice these two graphs actually still are reflections over the line y equals x. It just so happens that when I look at the inverse, I don't get a function because it doesn't pass the vertical line test. So it is still possible to have an inverse relation, just one that isn't a function. Next, we'll graph functions and their inverses. We've already seen this a little bit, so this shouldn't be too different. So notice that in all of our previous examples, the graphs were mirror images over the line y equals x, so they're symmetric about the line y equals x. Remember, in order to create an inverse, we just swap the x and y coordinates. So even if we don't have a formula for the function, we can still draw the inverse. Here are two examples that are already fully graphed out. We have the f in blue here, and then we have the f inverse in red or pink here. And notice they are reflections over the line y equals x. They both pass through the point 1, 1 and 0, 0. Now this isn't quite a square root function and a square function, but does have a similar shape as that previous example. In example B, we have two lines. Now I want you to notice that when you have two lines that are inverses, they have reciprocal slope. So the blue line has a slope of up 1 over 2, so 1/2, and the pink line has a slope of up 2 over 1, so 2. So they have reciprocal slopes. Also notice that the y-intercept of one of the functions is the x-intercept of the other. That's that idea of reflecting over the line y equals x. So I have this point 0, 2, which becomes 2, 0 on the other one. I've got two examples here where we don't know the particular equations, and we're going to graph the inverse function. So we have the original function in blue, and we need to graph the inverse function. First place to start would be to go ahead and look at some of the ordered pairs. So now we have our ordered pairs there, and I will go ahead and just swap the x and y coordinates. So -1, -2 becomes -2, -1. 0, -1 becomes -1, 0. And 1, 0 becomes 0, 1. Right now, those just look like they're on a line, and we don't want it to look quite like that. The thing that we need to recall is that this function looks like a cubed function, so its inverse should look like a cube root function. So when I'm drawing this, I'm trying to make it look like a cube root function. They should also be reflections over the line y equals x. And it turns out that we actually already did this problem algebraically. This function happened to be f of x equals x cubed subtract 1, and the inverse function was f inverse of x equals the cube root of x plus 1. Notice with transformations, we have shifted the cube root function left 1, whereas on f, we have shifted the cube function down 1. This next example looks like it's some sort of piecewise function because I've got two different pieces of lines. Again, we'll select a few points, label them, and then swap the x and y coordinates. I've got 4 points labeled there on the original function, and now I will just swap the x and y coordinates. -3, -2 becomes -2, -3. I'll go ahead and do the rest quickly, and you can pause and then see if you get the same thing. So here's our inverse function. Notice that the original first piece of the function had a slope of 1, so the inverse would have the reciprocal slope, which is also 1, so we're getting a slope of 1 here. And then the original function's second piece had a slope of 1/2, and the inverse function had a slope of 2. And I knew just to connect the inverse function with lines, since the inverse of a line is still a line, so I just had everything with line segments. Our last objective is to determine whether two functions are inverses of each other, and we'll do this using function composition, which we learned in the last section. Our basic principle here is that if a function is 1-to-1, then the inverse of f is f inverse, such that if I compose f inverse with f of x, I get x, and if I compose in the opposite order, so actually if I do f of f inverse of x, I also should get x. So this should say equals x for all x in the domain. What I want you to think about when we're doing functions and inverses is if I do a function f that means I'm putting x into my input-output machine, and what I'm getting out is f of x. Now, if I go back in backwards, that would be the f inverse function, but I should still be getting x out of that. So if I put f of x into f inverse, I should get x, and it should work in both directions. So when we're doing compositions, we don't really have two function machines. We really only have one function machine, and it's just a matter of whether you're going forwards versus backwards. So we're going to show that two functions are inverses. My f of x is 4x minus 1. My f inverse of x is x plus 1 over 4. And we have to show the composition in both directions. We'll start by doing f inverse of f of x. And I'm going to go ahead and just put this straight into function notation. F inverse of f of x would be putting my f of x function wherever x was in my f inverse. So my f inverse function was x plus 1 over 4, and I've just left a space there, and I'm going to put my f of x function, which is 4x subtract 1, in where I would normally have the x in my f inverse. Then I just simplify. In the numerator, I have a -1 and a +1, which zeroes out, giving me 4x over 4, which just equals x, as desired. We're going to do the opposite composition order on the next slide. Now we need to do f of f inverse of x. So f of f inverse of x means wherever there was an x in my f function, I am going to put in my f inverse. So I'm taking x plus 1 over 4 and placing it in the x place of my f of x. We can cancel out a 4, giving me x plus 1 subtract 1, and then cancel out or zero out the 1 and the -1, giving me just x as desired. So that is the end of inverse functions.